That'd be fun, eh?
No.
There we go. Okay, good. Good, good.
440
4:40. 4 minutes and 40 seconds.
plus like the million I took you before. You're broadcasting, aren't you?
Yes, we are broadcasting. We're broadcasting at continuity. Okay. So you notice there are a few kinds of discontinuity. Okay. So basically, continuity really just means that you can run your pencil, along the function forever, and you don't have to pick up your pencil. Okay, so there's no holes, there's no places where we have to jump. So this is continuous. This is a continuous function. Okay, and there are lots of examples of continuous functions. So for example, the exponential function. It is continuous everywhere. You remember the exponential function? Even though it looks like it has these really crazy behaviors, there aren't any breaks in it anywhere. Okay. Similarly, there's the absolute value function. All right. So that was the one that just says, I don't care what number you put in for x, I'm always going to put out the positive value for that number. So the absolute value function, as long as we don't do anything to it, okay, turns into that. But -5 is 5. Looks like a v. Now, interestingly enough, the absolute value function actually has a place where the derivative doesn't exist. In spite of that, it's continuous everywhere. And then other examples, polynomial functions, they're continuous everywhere. What's an example of a function that is not continuous, often has a discontinuity in it? The rational function. Okay. So there's the rectangular hyperbola, the reciprocal function, all of its cousins, okay? This is an infinite discontinuity. At x equals 0. It heads off for negative and positive infinity, and there's nothing we can do about it. There's no going back for this function. It is discontinuous at x equals 0. Anywhere, even if you translate this, okay, you're going to wind up with an infinite discontinuity somewhere. Nothing we can do. All right. But there is this other thing that's known as a removable discontinuity. Okay, so a removable discontinuity means that we can actually just sort of fudge when we get to this one value. So here's an example of a function that has a removable discontinuity in it. Okay, so x cannot be equal to 1. With this function, or we wind up with that 0 over 0 condition. And so this has a point of discontinuity at x equals 1. But unlike this function that's just a basket case at the discontinuity, this function, if we just redefine it at one point, it's going to be okay. Now, the official definition of this continuous So this is the technical definition of continuous. So a function is continuous at x equals a if the limit of the function as x gets close to a exists. And just remember that means the limit from the left is equal to the limit from the right. And so this one definitely fails. It's going to infinity, but the limit from the left and the limit from the right definitely aren't equal. And the limit as x approaches a is equal to the value of the function at a. Okay? And so as we approach this point from the left and the right, not only are the approaches the same, they're also equal to the value of the function at that point. And so this is interesting if you graph it on Desmos, because these sort of cancel out. Okay, and you just wind up with the leftovers, plotting the leftovers. And so it is a straight line with a slope of 1 and a y-intercept of 1. Okay, so it's really, let's call it g of x. That's what the function looks like. Unfortunately, f at x, on the other hand, has this tiny little hole. Has this tiny little hole right there when x is equal to 1. So we call this removable because we can actually come up with a value for the function right at that hole if we want to make it continuous. We can actually fix this issue we have with the hole. And so what we say, we actually turn this original definition so we say, well, our function is equal to this rational thing. For any real number, just as long as we stay away from positive 1. And now we have to fill in the hole. In other words, we have to figure out a value for the function so that the limit from the left is going to be equal to the limit from the right. And we're going to fill in this hole with the value of the function that would go in there. Okay? So when x is equal to 1, let's pick a value that's going to fill in that hole. Any ideas what value we can give the function to fill in the hole? 1 would be right there. We would still, yeah. So we could say that the function is equal to 2 when x is equal to 1. In other words, all we really have to do is plug a 1 in here, right? Put a 1 in for x. In other words, put a 1 in where the discontinuity is, and just look at what value that gives us for the function. And then we know we've got it. It's going to match up left, right, and when the function is exactly equal to this discontinuity. Okay? So they ask you questions sometimes. What value do you need to add to make the function continuous? Basically, you're just filling in. You're going to be filling in a hole. The other thing you might potentially be doing, if it's a piecewise function, you might be finding a value for a parameter so that the two functions meet up. Last kind of discontinuity. There is another one. They show you the CEMC materials. They talk about this oscillating discontinuity. It's a kind of a manufactured function that goes, gets very, goes back and forth between values. The last one we'll look at, though, is the jump discontinuity. And so this comes up with piecewise defined functions. And so we might say this function is x plus 1 squared minus 1 if x is less than, I don't know, 2. And then otherwise it's x plus 4 if x is greater than or equal to 2. Okay? Open circle means the point is not included in the line. Closed circle means the point is included in the line. This is a piecewise defined function. Hopefully they don't meet up. 2, 4, oh man. This one actually does not have, there, I fixed it. That was actually continuous, that function, but I think I fixed it now. So that's 4, 6, no, I actually broke it again. I can't believe this. No, it's good. It still has a jump discontinuity. It just doesn't look like the way I thought it did. Okay, anyways, that's the last kind of discontinuity. That's it. The only other thing that might happen is they might say, what is the value of A to make this function actually continuous? And so we'd just be interested in looking at x when it's equal to 2, when the exciting things happen, okay? When x is equal to 2, we want to make sure that this function is equal to this function, and then we've got them coming from the left and the right the correct way. And that's all going to happen. The excitement's going to happen when x is equal to 2. And so we'd be saying 2 plus 1 squared minus 1 is equal to 2 plus a. And we just have to solve for a. So this is going to be 9 minus 1. Make it nice big 9. It's equal to 2 plus a. Thus, I have fixed the jump discontinuity. This piecewise defined function is now continuous if I choose a value of 6 for a. That's it.